An equilateral pentagon AMNPQ is inscribed in triangle ABC such that M lies on AB, Q lies on AC, and NP lie on BC. Let S be the intersection of MN and PQ, and denote by L the angle bisector of MSQ. Prove that OI is parallel to L, where O is the circumcenter of triangle ABC, and I is the incenter of triangle ABC. We can solve this geometry problem using complex numbers. Complex numbers are a useful way to learn more about triangle ABC in configurations like these, and I highly recommend you go check out my friend's YouTube video on complex numbers, which he uploaded yesterday. The link is down in the description below. Click the link and it'll send you to his YouTube video. It's called Using Complex Numbers to Solve Real Problems. Anyway, as always, in triangle ABC here, we assign its circumcircle to the unit circle, which has center O equal to 0 on the complex plane. And incenter I, we want to prove that OI is parallel to L, so we need to label the incenter I of ABC. Now, there's no easy way to get I in terms of A, B, C, and other points here, so we have to turn to the arc midpoints of AB, BC, and CA. The arc midpoints opposite A, B, and C I will label as MA, MB, and MC respectively. Now, recall from EGMO that the orthocenter of triangle MAMBMC is the incenter I of ABC. And in complex numbers, if the circumcircle of any triangle coincides with the unit circle, then the orthocenter of that triangle is simply given by the sum of the complex numbers that correspond to the vertices of that triangle. So in this case, point I is equal to MA plus MB plus MC. Let's focus on equilateral pentagon AMNPQ. Equilateral means all 5 sides have the same length, but it is not necessarily true that all 5 angles are equal. It just means all 5 sides have the same length. Let's call that T. So AM equals MN equals NP equals PQ equals QA equals T. Now you might be thinking, what do the arc midpoints have anything to do with equilateral pentagon AMNPQ? Well, if you draw the lines from O to each of the arc midpoints, they will be perpendicular to the sides of ABC, and 3 of the sides of triangle AMNPQ coincide with part of each of the sides of ABC. So if you draw an OMA, that's perpendicular to BC, and therefore also perpendicular to side NP, which has length T of equilateral pentagon AMNPQ. The same is true for the other 2 arc midpoints. Let's draw them in. OMB and OMC are perpendicular to QA and AM, respectively. Now, recall that given any 4 different complex numbers, A, B, C, and D, then AB is perpendicular to CD if and only if D minus C over B minus A plus the complex conjugate of D minus C over B minus A equals 0. So if this D minus C over B minus A is equal to P plus QI for some real numbers P and Q, then this would have to be equal to P minus QI. That's what this is saying. So the QI's cancel out, and we have 2P equals 0. That just means P equals 0. So the real part of D minus C over B minus A is equal to 0. And that just means D minus C over B minus A is equal to some I times a real number. So let's apply that for each of OMA, OMB, and OMC, and sides NP, QA, and AM of equilateral pentagon AMNPQ. So going down, we have P minus N over MA minus O is equal to I times some real number because NP is perpendicular to OMA. And that real number is just the modulus of P minus N over the modulus of MA minus O. I don't have to write O because that's equal to 0. So this is equal to I times T over the modulus of MA, which is just 1 because it lies on the unit circle. So at the end of the day, this is just IT. So we can write P minus N over MA is equal to IT. Now we can also write A minus Q over MB minus O, but we don't need to write O because that's equal to 0. A minus Q over MB is equal to IT as well, because QA is perpendicular to OMB. And finally, we also have M minus A over MC is equal to IT. So now we have three fractions, P minus N over MA, A minus Q over MB, and M minus A over MC, which are all equal to the complex number IT. So we can add the numerators and denominators of the three fractions, and we can still expect the result fraction to be equal to IT. We have P minus N plus A minus Q plus M minus A, so the A's cancel out, over MA plus MB plus MC is equal to IT. So this just says that M minus N plus P minus Q over MA plus MB plus MC is equal to IT. And all this means is that M minus N plus P minus Q is going to have to be perpendicular to MA plus MB plus MC, which is just OI, because MA plus MB plus MC is the orthocenter of triangle MA, MB, MC, and that's just I. So M minus N plus P minus Q is perpendicular to OI. But what else is M minus N plus P minus Q? Well, if you rewrite that as M minus N minus Q minus P instead, well, that's just equal to Mn minus QP. You can think about it as a difference of vectors. And that difference, Mn minus QP, we know that they are both equal in modulus. They both have modulus T. Mn minus QP is going to lie perpendicular to the angle bisector of angle MSQ. For a simple explanation of why this is the case, we take vector Mn here and QP here and move them down so that their tips coincide with S. They're still pointing in the same direction. But if we move them down here so that their tips coincide with S, we would still see the same thing with respect to line L, because they're still oriented in the same direction. And the difference of these two vectors will be this one over here, which completes the isosceles triangle. And the triangle is isosceles because, well, both of these have equal length. So this would have to be a right angle, and the third side is perpendicular to line L. That's still the case even if we move Mn and QP up here and they're still pointing in the same direction. So Mn minus QP is perpendicular to line L. And this is uniquely true because both Mn and QP have the same length. So we found that M minus N plus P minus Q is perpendicular to both OI and L. And if that is the case, then OI better be parallel to L, where O is the circumcenter of ABC and I is the incenter of ABC. Now, it must be said that it was never required for AMNPQ to be fully equilateral. In fact, OI would still be parallel to L even if MN and PQ were a different length U. All we needed was for the sides AM, NP, and QA to be equal so that the perpendicular condition could hold for MA, MB, and MC, and we could add up the three complex number fractions to get IT, and then we would be left with MN and QP, and the isosceles triangle condition, where the third side of the triangle is perpendicular to line L. That's the only way for that to happen. They never had to be both equal to the same thing as AM equals NP equals QA, though. Yeah, I thought that was pretty interesting. that we never needed AMNPQ to be fully equilateral. OI would still be parallel to L if AM equals NP equals QA and MN equals QP. So thank you all for watching my YouTube video. I hope you enjoyed, and please follow my channel if you would like to see more videos.